you. Okay, so this is a joint work with Itai Arieli and Fedor Sandomirsky. The plan of the talk, I will start with presenting you a constructive, a construction of a constructive Blackwell theorem, which is essentially a construction of a signal that garbles information whenever it's possible. And then I will show you some application of this. In particular, we will see what is special about the specific garbling that will be suggested. Roughly speaking, it will maximize optimism in dynamic learning setting or dynamic persuasion, whichever angle you want to look at. Okay, so Blackwell has quite a few theorems, so let me start with saying which Blackwell theorem I refer to, and let me start with the definition of majorization. Okay, we have two distributions that and there with CDF F and G. And we say that F majorizes G if this inequality of integrals holds pointwise for all values x. Okay, so this is a definition. Just to get the idea how central this object is in economics, you can look at how many different equivalent names it has. So majorization is one. It's the same thing as second-order stochastic dominance. It's the same thing as mean-preserving spread. It's the same thing as also called as convex order, Lorentz order, less risky if we think of these things as outcomes. And more related to this talk, it's also called that less informative, that F is less informative than G. And in the context, it's also called Blackwell order because Blackwell was the one to kind of to point out a connection of this inequality with more or less informativeness. Okay. So now let me introduce you the Blackwell's theorem. So we have a real valued state space distributed according to the distribution G, which will be the more informative one. S is an abstract set of messages, a signal about the state is essentially a mapping from the states to some distribution of signals. Okay? And now what we want to, the object that we want to look at is the induced distribution of the posterior means. Okay, not of the posterior, right? The posterior is a distribution over the reals. And we want to look at the distribution of posterior means. So the induced distribution of posterior means is the distribution of the what is the expectation of the state conditional on the signal when S is drawn, when the signal is drawn in two steps. First, we draw a state, and after it, according to this mapping pi, we draw S. Okay? Why I call it more informative, less informative? Because this story also has an interpretation in the context of binary states. Okay, so think that you have two metastates, H and L, and a partially informed sender whose belief of the partially informed sender is distributed according to this function, to this distribution G. This is the probability that the sender, the more informative one, assigns to the state H. Okay. Pi, you may think of pi as sender signaling policy, what he decides to inform, to tell to the receiver. And now notice that the expectation of theta, conditional on what he observed, is exactly receiver's posterior about theta, right? This is just because Bayesian updating is the linearity of, okay, so this is why you essentially can think of G as more informative information of the sender and F as the less informative information of the receiver. And here is Blackwell's theorem. It says that F majorizes G. I remind you, this is this inequality in the integrated CDF space, point-wise majorization. If and only if there exists a signal that induces the distribution of posterior means F. Okay, obviously, if we start with the partially informed sender whose information is G. Okay, this is Blackwell's theorem. By the way, Blackwell has several related results, but about more informativeness and less informativeness. But this nice connection between kind of an algebraic terms, just integrating the CDFs, valid only in one-dimensional spaces. There is no analog for that in higher dimensional spaces. Okay, so, and in particular, this talk is about one-dimensional spaces because there is no analog for this theorem for higher dimensions. How did Blackwell prove this result? Yes?
So what I don't understand is, isn't that non-symmetric in what is the high and the low signal, or is it? I mean, so it's, if you have a uniform distribution, I would think that's very uninformative, but if you have one-point distribution, it's very informative. But the inequality with the integral seems to suggest that it only goes in one direction. Or do I misunderstand? Is that my question?
So it must satisfy the expectation should be equal. So for instance, the inequality at the end is always exactly one.
Again, uniform distribution is, I mean, very informative, and if you have a one-point distribution,
is concentrated at the half. Yeah, so it's the integrated CDF is 0 up to the point 1/2, and it go. Yeah.
that's what it is.
Yeah. This was my first. Okay. So one direction is Jensen's inequality, that if you get a distribution, then you must have this majorization property. The other direction is proved by some duality argument or equivalently some separating hyperplane argument. But crucially, this second direction is non-constructive. They just show the existence via some non-constructive duality argument, and our contribution in this respect is to provide an explicit constructive proof for this direction. Namely, we will specifically say which signal we want to send to garble information G into information F. Okay. Just an illustrative example. So let F be the beta 1,1 distribution. This is a distribution whose density is x times 1 minus x multiplied by the appropriate constant, so that the integral will be 1. And G is the uniform distribution. We can see from the picture that F is more concentrated around the mean. So it's more, it looks that G is more informative than F, okay? And what Blackwell says, he said, okay, look at the integrated CDF, okay? So I'm doing double integration and then second integration, and we get this plot, okay? And we can These are simple formulas, and you can verify, yeah, indeed, F is pointwise below G, and therefore, indeed, G is more informative than F. Okay, now my question, how...
F is more informative than G, right?
Again, sorry?
You said G is more informative than F.
F is more informative than G, right?
F is... No, G is more informative than F, right? The most less informative thing is, let's say, an atom at 1/2, right? Because it means that no matter what, you have the same posterior. So as you are more concentrated around the center, you are less informative.
These are distributions of beliefs, not of signals.
Yes. These are the distribution of beliefs. Yeah. Yeah. Those are the distribution of the posteriors. Yeah. Okay, but now it still remains the question. Okay, you start with this distribution G. Which signal you need to send to the receiver so that his belief will be F? His distribution of belief will be F. Okay. So here I want to, essentially what we suggest is one specific way of garbling things, which is via a downward uniform signal. Okay, so what is the downward uniform signal? It is specified by a real valued function. Okay, there is one monotonically increasing real valued function. And the procedure, think of this space as the space of theta, okay, of the state, the continuous, the real valued state. What we will do at state theta, we will draw uniformly at random, a number in this interval, and call this number the drawn number S. And we will send S to the receiver. Yeah. Now let's think from the perspective of the receiver who doesn't know theta. What he observes essentially, he essentially, okay, this is the places in which I can get the signal S. Okay, and so this is a downward, the notion of downward uniform signal. Let me highlight some properties of downward uniform signals. So we just saw that essentially what the receiver will believe, his posterior belief, which is a distribution over R, will essentially be supported on this dot interval. And notice a special property of downward uniform signals, which is identical quantiles. What I mean by that, notice that since we take the distribution to be uniform, then the density at this point is exactly the same as the density at this point. So if I tell, essentially a way you can think of it, if you look at the distribution conditional on the signal 0, then all the other signals are essentially lower bounds on the realization of H. So this guy, for instance, I'm just telling him, look, it's not, this guy has no lower bound. It can start from 0, the one who receives the signal 0. And these guys, for a guy who got this signal, he will know that this is a lower bound on the distribution. So essentially, there is some single fixed distribution, which is the H minus 1 of which is the distribution conditional on 0, and I'm just sending lower bounds on it. It also relates to a classical German tank problem. Let me remind you or tell you what so in the Second World War, one could observe the serial numbers of the German tanks, and according to these observations, they wanted, and the Germans produced the tanks and gave them consequent serial numbers, and according to these numbers, they wanted to estimate how many tanks the German army has produced. So notice that when you observe a serial number, is exactly, you get a lower bound on the distribution. If you start with some belief about how much tanks are produced, and now you observe a tank, then essentially it tells you that now you condition your belief on another on a lower bound on the serial number that you had. Okay. So you may think also from this perspective. So these are downward uniform signals. So this is the constructive theorem. The first one is says, look, if F majorizes G, namely G is more informative than F, then you can garble the information G into the distribution of posterior means F using a downward uniform signal, the specific type of signal that I just described. So far, it doesn't look constructive, right? Because I didn't tell you what the function H is. Okay, the nice feature is that essentially here is a formula for the function H, and it's not the most trivial formula, but also not something too crazy. So this is an explicit formula for the function H, and let's just, so you do some integration and another function which plays an important role in the construction and also in the formula of H is the function alpha, which is the slope of this tangent. You start with at some point small t. You look at the tangent, the slope of this tangent will plays a crucial role in this construction. And we will get back to this picture. You will see it where it comes from. And
Sorry, what are capital T and T naught?
this so at this point you want to. Yeah, you want to see how you want from this point to take a tangent to the function g, and such, yeah.
And T naught is arbitrary.
Sorry?
T naught, the lower variable of integration.
No. You mean this part?
In the formula.
In the formula, alpha is this? T0. Thank you. So, okay. So, T0 is an arbitrary choice of a point. Notice that if you instead of choosing a function h, you choose a function 2h, for instance, it will not change anything. Everything is scale invariant. And you can notice that if you change T0, it just multiplies, since it's in the exponent, it just multiplies h by some constant. So it doesn't matter which point T0 you pick, just an interior point. Okay? So let's get back to this example, right? You can do the calculation. You start with what is capital T of small t, right? You start with what is capital T of small t. Just to show you, you do the math essentially, and you get that the function h should be t to the power 3 over 2. Okay, so this is now provide a constructive way to garble the, let's say, uniform distribution to the beta 1, 1 distribution. Let me give you another example, which we will get back to it later. Think of the more informative signal as being the uniform over 0, 1, and the less informative one being a distribution over two atoms at 1/3 and 2/3. So essentially what the downward uniform signal suggests is, think of these lines as the realization of theta. Okay, so we have uniform distribution, so it's the same length everywhere. So this means that all the values between 0 and 1/3 will be contracted to the point 1/3. It is insufficient, right? We need it to be mean preserving. So additionally, all this blue mass will also be contracted to 1/3, and the red mass will be contracted to 2/3. Okay, so this is what. How can we see that this is what happens? Look at the identical quantiles property, right? We want that the quantiles will be identical for every point, and this is the picture that will be created. I just want to notice that this is obviously not the only way to garble information, right? We have a huge space of different other garbelings. Here is one more example, maybe more natural, but we can contract all the values between 1/12 and 7/12 into 1/3, and the remaining part will be contracted to 2/3. Okay, so, and you have infinitely many other options. So we definitely not try to say that the downward uniform garbling is unique. It's just one that has a clean formula for it. Okay, clean can be done here. Another nice feature of downward uniform signals is their nice interplay with conditionally IID setting. Assume just that you want now the receiver will not observe just a single signal. By some reason, I know that he will observe k IID samples of signals, like in the German tank problem, right? We do not observe just one tank. We observe some of them, and all of them are IID settings of this. And now we want to induce the distribution F from the distribution G, not via a single signal, but by some procedure of k IID, conditionally IID signals. Can we do it? No problem. Take instead of the function H, which we know that, the proposition says that a single downward uniform signal with the function H is equivalent, namely it induces exactly the same distribution of posterior means. In fact, it even induces the same distribution of posteriors, not only of posterior means, so it's equivalent to k IID downward uniform signal with what you should do to the function, just take the kth square root of it, and we are done. So it has very nice multiplicative interpretation. And if you think of it, sometimes working with conditionally IID signals not always is as simple as it is here, but here it turns out to be simple. Okay, so.
Do you have a sense of what this set of signals with these properties? Sorry, set of garbelings with these properties? Is this uniquely pinned down in your construction? Probably not, right? Or maybe it's almost. Or, right?
Any H, you can take the square root. You have an example on the previous slide.
But then you're still in the downward uniform class, right? So I was wondering
if for other garbelings there is an analog of this proposition.
There are other classes of garbelings that still have this property.
I would say overall it's not. It's something very special to downward uniform. So I would expect that the answer will be no, but I do not commit to.
It seems special to hospital.
Yeah. The reason, right, because in the German problem, essentially you always get lower bounds on something, and this is essentially a reason why getting IID lower bounds is something that essentially creates another one lower bound, and this is why essentially it's possible in this case to play nicely with conditionally IID signals. Okay, now I want to ask what is special about the specific garbling, right? When I said that we garbled G to F, essentially we created some correlation, some coupling between the realization of G with the realizations of F. And as we saw, there are many ways to correlate those. And the question, what is special about the one that we suggest? So let me tell you a story of persuasion. You may also interpret it as just story of agent who is dynamically gains information and learns the state over time. So here is a story of persuasion. We have two meta states, H and L. We have a partially informed sender whose belief is theta. We have also partially informed, but less informed receiver who starts with a belief F, okay? And right, since he's less informed, then F majorizes G, namely G is, the sender has some informational gain over the receiver, so he has something to sell him, namely, right? He can tell him things that he doesn't know, but he's not, unlike the standard case is that G is full information and F is no information. So we study, both of them are partially informed, okay? And sender reveals information over time. So now how can we refer to an information over time? So essentially a splitting lemma in one shot tells you that it should satisfy the martingale property. So if we think of continuous information revelation, then there is one-to-one correspondence between sender's policies over time and martingales, right? He essentially induces martingales of belief for the receiver. What this martingale should satisfy, according to what we said, the initial information is F. The terminal distribution, right? The sender cannot tell more than he knows to the receiver. So the terminal distribution should be weakly less informative than G. And in our story, think of a receiver who has an irreversible option of adopting. Think of it as a vaccine shot for corona. So once you take it, you cannot regret. And the sender wants the receiver to adapt, okay? And the receiver has some threshold above which he prefers to adapt, okay? So if his belief is about 3/4, he will adapt, but not less than that. And here is kind of somewhat, at the first look may look weird assumption, is that receiver adapts in this continuous process if at some point of time his posterior passed the threshold 3/4, he immediately adapts. Okay, why it's weird? Because why shouldn't he wait, right, and gain more information? And one rationalization for this can be in kind of more, you can come up with a setting in which it will be rational. For instance, if you think of it in a very long time interaction, not in the 0-1 interval, but in a very long, and if the sender is patient, he doesn't care when the adoption will happen, but the receiver is impatient, then if the sender will reveal information very, very slowly over time, then the receiver will tell himself, okay, I can take adoption now or wait. What will happen if I will wait? Maybe one day I will know much more, but till then, my discount factor is already very bad, so I will be better off adapting now. Okay, but you can also just refer to it as a behavioral assumption that once it passes the threshold, it is done. So first of all, I'm not sure it's immediately from this story, that in this story, the correlation of f and g, I just told you I didn't, plays a crucial role, okay? If the sender is the one to design this correlation, the downward uniform is his best choice, okay? So this is the unique best choice. Unlike him before, this is the only, okay? So, and one more important aspect that I want to notice, I want to think of the sender as one who doesn't really know theta, this threshold. So, for instance, you can think of it that he faces population of agents and every one of them has a different theta, and I want to convince many of them, as many as I can, to take the vaccine shot. So theta is not knowledge of the sender. So now let's first look at the case where this correlation of f and g is exogenously given. And no one controls it. And let me suggest a policy. It's called, we call it gradual revelation of bad news. What it does, so at time t, we reveal to the agents whether their realization is in the interval 0t. If it is, he perfectly knows the state. If otherwise, he just have a lower bound on the remaining distribution. So no further information is provided. Okay, a policy, a proposition, or you can even call it a theorem. Essentially, it essentially has been proved by Dubins and Gilad in '78. That, and in a moment I will tell you how they formulated it. That for every given correlation, this policy maximizes the probability of adoption simultaneously for all thresholds. Okay, so it's universally best policy for all thresholds. So Dubins and Gilad proved this result for a Dirac measure f, where f starts. Dubins and Gilad, I don't think, when they wrote this result, they were not concerned about persuasion problems. But what they were concerned of, and this is, I think, very nice mathematical object, is the object of maximum martingale. Okay? So we want, given a martingale, every martingale, his realization induces essentially a distribution over its maximum. Okay? And now we want to ask, can we control this maximum sometime? Which distribution of maximum can be induced?
You mean maximum over t, yes?
Maximum over all the time, yeah,
So
all
on
the
each
realization.
On each path, you look at the maximum of the path.
Yes.
Okay.
Yeah. Okay. So essentially, you can see that the problem of adoption is equivalent to saying that the maximum of the martingale was above t once we assume this immediate adoption. So essentially what we do is apply essentially this result. It's just a reformulation of the results, but we do it pointwise for every realization of f. Okay? Now you can compare, for instance, here I plot what happens for every value tau, what is the probability of adoption. So for low values, for this correlation and for this correlation. As you can see, it creates two different plots. But another very nice feature, that the green one,
the left one, yes?
Green is the downward uniform one, yes.
Yeah.
This is the green, and in black you see, and this is not a coincidence, okay? What we show is that essentially the correlation that we have induces the downward uniform signal, induces the best probability of adoption, and we also give a formula for this probability of adoption, which is exactly goes back to this picture. And yeah, unfortunately, I have no time to talk about the proofs. So yeah, just I think, yeah, okay.
So we have time for a couple of questions, and I will let Yakov pick up the question.
Yeah.
Great. What about higher dimensions? So maybe 3 basic states instead of 2.
Okay, so as I said, this specific Blackwell's theorem has no analogs in higher dimension. You cannot write the condition of f being mean preserving contraction of the other as some inequalities of integrals. When I say we cannot, it's not only that no one came up with such inequality so far. There are evidences for that that comes from the extreme points of this set. It has too many extreme points that such that if by contradiction we would be able to come up with some simple inequalities, then it will contradict the fact. So the mean preserving contractions in one dimension is very elegant object characterized by these integral inequalities, and in higher dimensions it is not. And therefore it's.
Why do you need it? Just define it. Just define it as one-step martingale. Forget the inequalities. What's the problem with that?
No.
One step in a martingale, yes? It's, when you go from prior to posterior.
Sure. No, I'm not.
You don't have the, the inequalities on the distribution functions, that's just a tool. Forget about that. Can't you? So
you ask, but if I understand correctly, the question is whether we can come up with a constructive formula for.
The point is that you have just a cumulative distributions or the distribution functions, and you want from that to construct. That's your data. Yeah.
Yeah. So, but in the computational aspect, it all boils down to some linear program. But the question how this linear program, how easy to solve it in infinite, in infinite dimensional spaces, obviously, you can do it by solving, but the nice feature here is some explicit formula for, explicit recipe for doing it, namely providing the result of this, a formula for the solution of this linear problem. What I try to say to Vincent is that at least the techniques that we have, they heavily rely on these figures of the integrated inequalities. Since we don't have such an analog for that in higher dimensions, at least these techniques will not cannot be adapted.
Okay, one more.
So this is a stupid question, but I don't understand where this, in your high-low example, the mean preserving property assumption is fulfilled. Where is the mean preserving for the two informed, for the sender and the receiver? You made an assumption about mean preserving, but I don't know.
You mean even at the very beginning?
No, the one where you talk about persuasion. You make an assumption about mean preserving, but what does it mean to be mean preserving with two states, high and low?
Okay, so what is mean preserving is that, right, so high and low, think of them as metastates. When I say that you have, that the sender has a distribution G, what I mean is that sender is partially informed. He doesn't know the state. He has a belief about the state. A belief about the state, I capture it as a real number.
But that doesn't have to be mean preserving, because that wouldn't make
well,
sense.
So
okay,
since
sure.
this is G, the distribution of the sender.
Yeah.
Now he sends some information to the receiver, and receiver, after absorbing this signal, forms a belief about the state, which is again a real number between 0 and 1. And it's necessarily must be the case that F will be a mean preserving contraction of G, not yeah, or in other words, G will be a mean preserving spread of F
For any signal that you send.
for any signal.
I
that
see.
you send.
Okay.
Okay, let's